A fundamental ingredient you need to describe physics all the way from particles to galaxies and beyond is curved 4D spacetime. What is curved space? Let's have a look at 2D space. That's flat, and that's flat too, that's not flat. What does it look like if it has constant curvature? You'll get the surface of a ball, a sphere. Let's have a closer look at the sphere we live on. If you move straight on a curved surface, you encounter phenomena that you can interpret as force. To describe these, you start with a metric, a kind of generalized Pythagoras that works for curved space as well. In the simplest cases, the entries are just numbers, that is, dimensionless. The second derivatives of the metric give the field equations that include an equation for energy density. The curved 2D space is embedded in the flat space of next order, 3D, where you can use ordinary Cartesian coordinates. The sphere doesn't care at all if it's described in curved 2D or flat 3D. That works in any dimension. It's called Campbell's theorem. This way of thinking is often discouraged, but it's a math identity. Do whatever serves you best. Up to here, this is a very general concept. To specify the type of force, you need an appropriate constant with appropriate units. For gravitation, Einstein used Newton as the limit case of weak fields, which gives a term with the constant of gravitation in the field equations of general relativity. Kaluza in 1919 showed that you can use such a formalism to describe electrodynamics as well. In his metric, the electromagnetic potentials A are inserted and a fifth dimension component phi is added. Kaluza used the formalism to get both the field equations of gravitation and Maxwell's equation. To get this, he had to assume a constant of gravitation term to get dimless terms A in the metric. There's no need for that. In fact, you might use a unit system that gives dimless terms right away. Anyway, in any unit system, a set of electromagnetic constants has to counter units of length to yield dimless terms for A. So, in the following, no constant of gravitation in the metric. The 5D space is assumed to be flat, so nothing extra compared to curved 4D spacetime, no extra dimension. The equations are solved for an electrostatic approximation. And that will give you an expression for energy density featuring a product of a point charge potential and an exponential for the fifth dimension component phi, that you can integrate to get an energy in the particle range. This involves some Euler integrals and gamma functions. For precise particle energies, we'll need an integration limit, sigma, obtained from a boundary condition, spin 1/2. That will give a value for energy of a neutral particle in the range expected for neutrinos. Charged particles should have higher energies and thus need a coefficient smaller 1 in the exponential, called beta in the following. You can calculate beta using, for example, the gamma functions, but here I want to discuss a numerical calculation in some detail. That's the calculation with boundary condition spin 1/2, that is the z component of a fermion spin. You have columns for radius, exponential phi, incremental energy, and a semi-classical calculation for angular momentum. The equations are given here and in the article. That's an important parameter, elementary charge over electric constant. If the electric potential in the metric is dimensionless, this has dimension length. Otherwise, this is of course independent of the unit system. Beta will be dimless. You can use that to calculate particle energy. The values will go to 0 for large r, but the spin contributions will be constant. That is, spin will define an integration limit. Let's redo this calculation and increase the integration limit until it hits the value given by the electromagnetic constants. Here we are. The particle parameters cancel and you'll get the value of a point charge. The value of spin, where this happens, is 1.73 times higher than before. That's root of 3. The maximum value for spin of a fermion. That is, we can calculate beta with a boundary condition spin of root 3 divided by 2. It's 4.9 up to minus 22. And that is absolutely amazing, since we'll see in a minute that beta is in control of the motion of stars in a galaxy. All of it. But the small things first. With beta and some minor assumptions, you'll get a set of converging series that span the range from the supposed range of neutrino energy to the Higgs energy. Here's a graph including the mean lifetime of particles and comparing with typical results from calculations with lattice QCD, the blue circles. The precision is about the same, but the Kaluza calculation needs no input of 3 parameters. It gives absolute energy values and doesn't rely on a reference. It notably covers all the stable particles, and it's worth to mention it again. It is a set of converging series that maps the entire energy range of particles. Let's go to the bigger stuff. Standard procedure, series expansion of the exponential. The first term by definition gives a Coulomb term, force, potential, whatever. In the second term, for distances beyond particle radius, spin and thus sigma should not play a role, and the r from the exponential will have no real values beyond the value that is defined by the limit for spin root 3 divided by 2. So this cancels the electromagnetic terms. That leaves beta as ratio of second order and Coulomb terms. For the interaction of 2 electrons, you'll need beta squared. That is 2.4 up to minus 43. You may recognize that number. It is the ratio of electrostatic to gravitational interaction of the electron. The second order term represents gravitation, as expectable. If the second term represents gravitation, the third term is expected to represent deviations from standard gravitation. You might think of dark energy and dark matter. The link between both and the preceding stuff is de Sitter space. De Sitter space is a space with constant curvature. We had that, and even a little bit more. You might interpret the sharp dents being due to local massive objects causing strong curvature. For example, electrons, protons, stars or galaxies. The third order term will add a de Sitter space centered at the center of the mass accumulation. There actually is a constant in the field equations of GR, the cosmological constant, lambda, that represents dark energy. It has to be strictly constant only if it is added to the equation. It does not if it originates from the metric term, as in the case given here. So it will be a limit value only. For dark matter, there's a well-known alternative, modified Newton dynamics, short MOND, that originates from the observation of a unique acceleration value, A0, featuring, for example, in the anomaly of galaxy rotation curves. That's the effect that the speed of stars far from the center of a galaxy in the range of weak gravitation approaches a constant value instead of 0. Of course it does, since we are in the de Sitter limit, featuring circular orbits. An intriguing relation between A0 and lambda exists, which unfortunately does not fit to the MOND expression. Let's see how this fits to the third order term. There's an unknown parameter here, the radius of de Sitter space. let's choose it to get the cosmological constant from this relationship. The value for r has some reasonable relation with electron parameters, so it's not a wild guess, but still a guess. I'll use it in a third order term corresponding to a gravitational acceleration term, so that I can get the square of the A0 star terms from before. That is, I used big R to fix the blue part to fit to lambda and A0 squared in the nominator. And if you do so, the red part, the remaining coefficients of the electron, give A0 as well in the denominator, which is not necessarily something that has to be expected. In the end, you get an expression that fits both Mond and the A0 lambda relation. And there is the possibility to do without fixing and to get rid of the ambiguities of the radius of de Sitter space by calculating the constant velocity of galaxy rotation curves. That has to fit the baryonic Tully-Fisher relation. Rearranging the equation of before without the R term gives the BTFR for one electron. All that's left to do is to multiply by the ratio of galaxy and electron mass, and there you are. Except for a minor gamma term, the relation is essentially just beta times speed of light up to the fourth power. And from this equation you can see that there is a dependency only on parameters of the electron, and the series expansion relation with gravitation and electromagnetism is obvious. In summary, elementary mass plus electrodynamics plus mass interaction, that is gravitation, plus deviations from gravitation are dependent on the same basic mechanism, curved spacetime, linked by a simple series expansion, and without free parameters, only with the electromagnetic constants, you can calculate particle-based phenomena that will cover about 50 orders of magnitude of physics with a precision between QD corrections and about a factor of 2.